So let's look at our first example of solving the time-dependent Schrodinger equation. So solving TDSE, example number 1. And for our first example, we'll take the simplest possible quantum system. This is called a particle in what we call quote-unquote free space, which is just really a fancy way of saying that the potential V of x equals 0 everywhere. There's no forces acting on my particle. Now, if we want to take our general solution, I want to turn it into a step-by-step program that you can always follow. So I'll go kind of slowly through this. It's kind of a simple-ish example, and I'm going to sort of belabor the point because I want you to really learn and see what the individual steps are. So for step number 1, that we were always going to be following, right, is we can't even actually write down the quantum principle of superposition until we know what those pure states are, right? Those are the central concept. So the first thing that we need to do is actually to solve the time-independent Schrodinger equation for the pure states. And of course, we're talking about pure states of the energy E, right? Once we have those, then we can use quantum principle superposition in our next step. But let's go through this step for our particular case. So say I have a particle in free space. Because it's in free space, for us in this example, right, we actually have the fact that the Hamiltonian is just the kinetic energy. It's just p squared over 2m. And our job then is to try to find out what are the pure states of energy in this particularly simple case. Now, so the pure states then for the energy are something actually that should be somewhat familiar to you for this particular case. So we're going to guess at them, right? Ultimately, we're solving the time-independent Schrodinger equation. But the only way to solve any differential equation, ultimately, right, is to guess. But here we can use our physical insights. So we want to guess for our pure states of energy E. Well, let's think about this. So I go and I've got some particle prepared in some state, right? And I keep doing measurements on this particle, and every time I do one of those measurements, I find that when I take the square of the momentum over twice the mass, I get back the same energy every single time. Now that should start to sound a little bit like some states that we've seen before, right? That we already are familiar with, right? If you think about it, I go in there, I measure the momentum of my particle, right? And every time, once I get that momentum and do p squared over 2m, I get the same answer. It really feels, in fact, like I'm looking at pure states of momentum, right? So our guess for the pure states of energy are going to be, in this case, that's only this case, it won't always work, right? In this case, will be pure states of momentum p. And as we know, we can always write P equals h bar k. And we are actually very familiar with what those pure states are, right? Those are the pure wave, e to the I kx over root 2 pi. Our whole, quantum slit experiment analysis led us to that final conclusion. And so we are guessing that these can play the role of our pure states of energy. So those are my phi of x. And now, of course, I need some kind of index in order to sum or integrate over these things, some way to label my states. And in this case, it seems pretty simple, right? The state really just depends on the momentum, or equivalently k. So for my index that I will be summing over, I will use just the wave vector k. This will be my summation index, where then k is nice and simple. It's a continuous real number, right, that varies continuously between minus infinity and infinity. So now that's our guess, right? But whenever we make a guess, we need to check our guess. So let's check. So what I need to verify is, in fact, what do I get when I apply my Hamiltonian to my pure state, phi k of x? And what I'm trying to check, hopefully what I get back is just some energy. And that energy probably depends on which state I'm looking at times my state phi k back again. Do I really just get a constant back again when I apply my Hamiltonian to my state? Well, I don't know. We have to see. So let's try it out. So the Hamiltonian, we've written it down so many times, it should be almost memorized. Minus h bar squared on 2m times 2 spatial derivatives, plus also whatever I get when I multiply my state by v. This is what I'm trying to compute, times, oh, not phi, but psi k of x, right? And I actually know what I'm guessing at for my phi k of x. Here's my guess, so I may as well substitute that in, save myself a little writing. E to the I kx over root 2 pi, right? That was my guess for my states, phi k of x. And of course, we're in free space, right? So we know our potential is 0, so that's nice. So this term goes away and gives me 0. So my job really then is to take 2x derivatives of this complex exponential. So let's write down what we have. So we have our prefactors, minus h bar squared over twice the mass, right? I've got my constant root 2 pi. I may as well just pull that out of the derivatives. And then what I have to put up here is 2 spatial derivatives of e to the I kx. Now, I think you guys know what we get whenever we take one of those derivatives, right? Any spatial derivative of an exponential gives me back my exponential, e to the I kx. And every time I take the derivative, I also get a constant that comes out. In this case, each derivative with respect to x pulls out those constants I k. And I'm going to do this operation twice, so I actually get I k squared. We'll go in for that term. And now you can see there's something nice, right? I squared, that's nice. That gives me a minus 1, but that will cancel this minus sign. So that minus sign goes away when I square that I. So all I'm left with, this is interesting, right, is some set of constants. I've got h bar squared. I've got a k squared from over here. Let's make sure I've got all my terms. Divided by twice the mass. And then all that's left, I took care of my constants, is an e to the I kx divided by square root of 2 pi. So yes, indeed, look, I've gotten back exactly what I was hoping for. Some constant that depends on k, yep, times my state back again. This is my state back again. And so therefore I can identify this is my state back again. So therefore we have a solution. We solved it. The time-independent Schrödinger equation. And the bonus that I get out is that these constants then tell me exactly what the energy is of the state I'm labeling k. So that is the energy of the state that carries label k. The energy is a function of the wave vector. Perfect. Okay, so that's step 1. We've solved the differential equation. The time-independent Schrödinger equation. So step number 2 now gets a little bit more complicated, right? So in step 2 now that we are armed with our solutions, we can actually construct the time-dependent superposition and this is kind of key, when we do that, we have to also, in this step, choose the weights. Okay, so let's try that. So we're going to construct our general time-dependent superposition, but then we choose the weights, right? So we've got our general time-dependent superposition. So we're saying then, in this case, psi of x and t, our solution, will be, now we know the general formula, we have to sum over all of our states. Now our states, as we've just said, are labeled by k, the wave vector, and k can vary anywhere from minus infinity to infinity. So I'm going to then sum over all those values, and I'm going to be indexing then by k, and that goes from minus infinity to infinity. Fine. So that's my summation. I then have to leave some space here for my weights. We will discuss what those weights will be in a moment. We have to choose those carefully. I've got my weights, w of k. Then I have to multiply by my states, and I know my states, so let's be explicit. I've got e to the I kx, right, divided by the square root of 2 pi. Those are my weights. Those are my states. And, you know, these are the phi k of x. I know I'm being very careful here. a little bit pedantic, but I want to make sure you guys get all of this. And then, of course, I have to multiply by our dates, which are our exponentials, which are e to the minus I. And remember, the form of the solution to make a frequency is it's the energy of the corresponding state divided by h bar before I can multiply by t to form a frequency. So I have to take my energies, which are here, and divide by h bar. So my energies have h bar squared in the numerator, so I'm only going to have one h bar in my numerator. The rest of the factor, as you can see, has got a k squared over 2m. That then is my frequency, which then, of course, has to multiply by time t. And this, again, this is the term I'm calling the dates, if you will. But it just really represents that time-dependent factor. Okay. So that's our constructed superposition. The only question here is, okay, what are we going to choose for our weights? Now, in general, the weights are constructed from this first decomposition step, right? This was here when we first wrote down the quantum principle superposition for pure states of energy E. I see I kind of expanded my screen here a little too much here, right? Like that. That looks better, right? These weights are chosen actually so that you reconstruct your initial state. So choosing the weights is kind of the same thing as choosing our initial state. Sometimes you're given your initial state, and then you would have to compute the weights that will give you that state. It may involve some kind of inverse Fourier transform, you know, something on those lines. But in this example, I actually wasn't very specific about what I wanted for my initial state. So the weights are kind of up to me a little bit in this case. That's my initial condition. So for my initial condition, I'm going to choose my weights. That's really what's choosing my initial condition. I'm going to choose. So what I want to make here, let's say, would be a little creative. For my weights, why don't we choose something that, you know, represents like a nice particle that has about a certain amount of momentum. So initial condition, choose a wave function, psi naught of x, that is mostly, or that is concentrated near some momentum near p equals, say, p naught, right? Which then defines for me h bar times some k naught equivalently, right? So I'll make my weights then some function that's peaked around that. I can achieve that by making some standard kind of Gaussian choice, k minus k naught squared, right? I'm leaving some space here to get the proper normalization factor, but what I'm saying is, you know, if I plot the magnitude of omega k squared, which are my probabilities, right, what I will get then is something that looks like a Gaussian as a function of k, and it will be sent, well, it looks like a Gaussian, it is a Gaussian at position k naught. So I'm going to make my initial condition have particles that have almost all the same momentum, something near this p naught h bar k naught. Right. Now, the one condition we have to be careful of course, is that when we choose our weights, we want to make sure that we've got this nice shape, but we want to make sure we choose a properly normalized wave function. So we have to make sure it's normalized. So for a normalization, what we need to happen is that 1 had better equal the integral over all k of the probability for any of those different values, which is my weights squared. In this case, that's going to be integral dk. I have to square this thing, and again, I'm leaving some space here for the normalization constant. And when I square this integral, I will double the exponent, e to the minus 2 sigma squared k minus k naught squared. Now, if I didn't have any factors here, we know what we would get for a Gaussian integral. We've done these so many times, right? If I didn't have any factors here, I know I would get the square root of pi. And the famous answer we get for this integral then is going to be the square root of pi over whatever here is in the numerator. Now, that won't be 1 unless I put the inverse of that factor here. That would ensure that I get 1. So I want to flip over pi divided by 2 sigma squared, and when I flip that over, the pi goes on the bottom, and the 2 sigma squared that was in the bottom goes into the top. So this statement now is true. This will actually integrate to the needed 1, and that tells me that omega squared, the weight squared, was the product of these two factors. So my prefactor then is the square root of this factor. So this weight then is going to be 2 sigma squared over pi to the 1/4 power. And now that I've chosen this as my initial condition, I can now put my initial condition into my weights up here. So for this example I'm constructing, this would be 2 sigma squared divided by pi to the 1/4 factor, so I get a proper normalization. And then my k dependence is e to the minus sigma squared k minus k naught quantity squared, like so. Those are my weights. Okay, now that then would be my solution. And I'm hoping, as I've been writing this down, you've been noticing that this starts to look very familiar to you, right? What this is actually is this is exactly the state that I gave you, the wave packet, the free space wave packet I gave you on the second problem set. Remember that big nasty problem that had complete the square and all these nasty things you had to do with it? I had promised you, though, that I didn't just make that up to torture you, right? That came from something very important. And what it came from was exactly this, right? So now you know exactly how it was constructed. It was constructed from concentrating my weights around a given momentum, right, with a proper normalization factor to make sure I obey quantum normalization. Those weights then were multiplying the states, which are pure states of momentum, and now you know where those came from, right, buried in our de Broglie hypothesis and coming out of our analysis of the quantum slit experiment. And finally, you know how these time evolution comes from a pure frequency associated with a pure energy, which comes ultimately, at least for photons, from the photoelectric effect, and for electrons from the combination of the correspondence principle and Hamilton's equations of classical motion. So you now know exactly where this function came from. So that's very beautiful. The final step then in any solution like this, and I don't want to belabor the point, but I really just want to break out all the steps that we follow all the time, over and over again in quantum mechanics, is, well, once you have your general solution, you want to then analyze. That's the final step, is the analysis. We want to analyze, right, the behavior of the solution, right? You guys, this is telling us now what the wave function is at any time t, right? And you guys are experts then from your quantum kinematics for taking such a wave function at time t and using it to compute all kinds of things. You can calculate average momentum, average position, the uncertainty in the momentum at a given time, the uncertainty in the position at the given time, right? The average position. And what you had done actually a while back, right, in the qualitative portion of the course, is you analyzed the peak location of this. So let's just review that quickly. I don't want to belabor it, but it's the kind of thing we'll be doing. So just to kind of complete the analysis, we would ask for maybe where is the maximum location of the packet at any time t. And we know how we would get that from stationary phase. So you could do a stationary phase analysis of this. And stationary phase says that 0 will give you the partial derivative with respect to k, evaluated at, of course, the peak contribution, the peak amplitude. These with the eyes, right, just give us phases, but the peak amplitude comes near k naught, so the derivative would have to be evaluated at k naught. We take then the derivative of the phase. Now the phase is not these amplitude real parts, it's only the imaginary parts, and there were two of them, kx minus this term, so it'll be kx minus then 1h bar k squared on 2m multiplying time t, right? That gives us the rest of the phase. We've collected all the phases. We can take the derivative with respect to k. The first term just gives me x, so this is the relation that will give me the peak position. Then I have minus the derivative with respect to k gives me an h bar k, right? There's a 2 that comes out, so divided by m, and then times t. But this is evaluated at my peak position, k naught, right? So this then tells me that x equals, and notice h bar k naught, that is just the main momentum, right? The most commonly observed momentum in my packet. So the x position then will just be that momentum divided by the mass, which of course is velocity, times time t. And that then behaves just the way we would expect a nice free space wave packet would behave. So that then completes our first example, but I hope you've seen by breaking this down into steps how you can go about solving any general problem in quantum mechanics that we might throw at you.